Hi folks, it's Dr. P. Just as we need to know how to convert to decimal, we also need to convert from decimal. Why do we need to do this? Well, mainly it's because we work with binary a lot in this class, almost exclusively in fact. So we certainly need to know how to go from decimal to binary. There are times when hexadecimal is really useful as well in digital engineering, so that's also something we need to know. In general, understanding how this process works from decimal to any random number system is a good skill to have in case the need arises in any other situation. Let's do a couple of examples. I want to make the decimal number exactly the same for each example and just convert to different number systems. We'll do each of the examples, and then at the end of this video, I'm going to circle back and make an observation about the results. In general, the process of converting from decimal is the opposite of the process of converting to decimal. So instead of multiplying by the base, we divide by the base. Each of the remainders is a digit in our solution. We stop when we get a quotient of 0. Then we just have to keep track of the order of each digit, making sure to keep the most and least significant bits in their correct spots. So let's convert the number 37,198 from decimal to 3 different number systems. First, let's convert to base 2, or binary. We're just going to iterate the process of division here, but we want to express everything in whole numbers. So 37,198 divided by 2 is 18,599 with a remainder of 0. We divide 18,599 again by 2, get 9,299 with a remainder of 1. Divide by 2 again, we get 4,649 remainder 1. Divide by 2 again, we get 2,324 remainder 1. Divide by 2 again, we get 1,162 with a remainder of 0. Continuing our division by 2, we get 581 with a remainder of 0. Divide by 2, 290, remainder 1. Divide by 2, 145, remainder 0. We're going to keep on going. Divide by 2 again, we get 72, remainder 1. Divide by 2, 36, remainder 0. Divide by 2, 18, remainder 0. Divide by 2, 9, remainder 0. Woof, keep going. Divide by 2, 4, remainder 1. Divide by 2, we get 2, remainder 0. Divide by 2, we get 1, remainder 0. Divide by 2 one more time, we get 0, remainder 1. Okay, so now we have a quotient of 0, so we can stop dividing. Yay, finally! I mean, we could keep dividing, but we'd keep getting zeros and more zeros, which doesn't add anything meaningful to our result. The last thing we need to do in order to actually stitch this together into a number is to figure out which of these digits is most and least significant, and then reconstruct our answer in order. The very first remainder that we got, way at the top here, is the least significant bit. In binary, our least significant bit essentially tells us whether or not our number is odd or even. The very last remainder that we got all the way down here is our most significant bit. So now what we're going to do is rewrite that number in order to get our binary value. It is 1 0 0 1 0 0 0 1 0 1 0 0 1 1 1 0. Second, let's convert 37,198 to base 7. Now instead of dividing by 2, we're dividing by 7. Again, we look at whole numbers and remainders rather than getting fractional answers. 37,198 divided by 7 is 5,314 with a remainder of 0. Divide by 7 again, we get 759 with a remainder of 1. Divide by 7 again, we get 108 with a remainder of 3. Dividing by 7 again, we get 15 with a remainder of 3. Divide by 7, we get 2 with a remainder of 1. Dividing by 7 again, we get 0 with a remainder of 2. We have a quotient of 0, so now we can stop. Identify the LSB, identify the MSB. Our solution becomes 2, 1, 3, 3, 1, 0 in base 7. Thankfully, that was a lot fewer division steps. Lastly, let's convert to hex. Again, we divide by the base. So 37,198 divided by 16 is 2,324 with a remainder of 14. Divide by 16, we get 145 with a remainder of 4. Divide by 16, we get 9 with a remainder of 1. Divide by 16, we get 0 with a remainder of 9. Identify the LSB and MSB. Now we need to create the hex value. But wait! Remember, we can only squeeze one digit into each bit. 14 is 2 digits. We solve this by using our decimal to hex conversion chart and noting that 14 becomes E. Therefore, this value is 914E. Remember how I said at the beginning of the video that I was going to make an observation about each of these results? I want you to notice the answers we got with each number system. Then, I'm going to fill in the blanks and show you what you would have gotten for each number system between base 2 and base 16. What you should notice is the compactness of each answer. That is, how many digits does it take to express this value? It took 16 digits to convert this number to binary, but only 4 to convert it to hex. The compactness of binary is pretty awful. It takes a lot of digits to express numbers in binary because the number base is so small. On the other end of the spectrum, hexadecimal is extremely compact because each digit really kind of contains 16 numbers inside. So there's a trade-off between number system and compactness. Unfortunately, our computers use a binary framework, so we're stuck with the limitation of the fact that binary is not compact. This means we need to use a lot of bits to store data. Maybe if we ever get quantum computing, which is supposed to be able to store 3-bit data, that may improve. But that's going to be a long way off. However, when we write code, which is something you might do in your future, you can make use of the compactness of hexadecimal and use it in your software code. So we are able to capitalize on this compactness in some ways, which is really nice. Okay, folks, so make sure you've practiced a lot of examples on converting numbers from decimal to other number systems. This is something we're going to be using time and time again in this class, especially with binary, so it really is a must-know skill. Until next time, stay well.